Hopefully you watched my previous video in which I created samples from my 16 blue spruces, because the results of that gave us a general idea in general of what this next topic is really all about. This is the central limit theorem, one of the most important ideas in all of statistics. And it's a little challenging to understand, so I'm really hoping you watch this video. So let's go through it. Okay? If we have a given population and its distribution, and we have calculated its mean, mu, and we've calculated the standard deviation, sigma, and we theoretically have all samples of some particular size, n, let's say. In my previous example, I took samples of size 4, but here it doesn't care what it is, size n. We took samples of size n from the population, and we calculated the mean of each of those samples. Just exactly like what I did with my previous video dealing with the 16 blue spruces. Now, the central limit theorem has two main points to make. Here's point number one. The distribution of the means of all these samples of particular size will take the shape of a normal distribution. If the sample size is big enough. Now, what do we mean by big enough? Well, there's two possibilities. If my original population has a normal distribution, then this may surprise you, but the sample size big enough, the sample size can be any size. And by any size, what do I mean? I mean any size. It can be anywhere from 1 to 10,000. The sample size doesn't matter. You will still get a normal distribution. Now, the bigger your sample size, maybe the more perfect normal distribution you'll get. But even with a sample size of 1, that'll work out fine. Okay? And the other possibility is that my original population that I'm drawing my samples from, what if it isn't normally distributed? What if it's flat across? Or what if it has maybe a dip in the middle? Or, it's just kind of strange looking. Well, if the normal population does not have a normal distribution, then in order for the mean of all the samples to take on a normal distribution, the sample size has to be at least 30. You say, where in the world do we get 30 from? Well, this can be shown and proved by using calculus. Don't think we want to try to prove it here. Okay? This is the first main statement that the central limit theorem has. The second statement is, well, let's go back and draw this picture again before we go on to the second statement. Generally, the distribution of the means of the samples of size n will be much narrower and steeper than the distribution of the original population. I showed you this before. Let's do it again. If my original population has a distribution like that is normal, with this being the mean, my sample means distribution, we will find most of the means will be clustered right around mu, the mean of the original population, and it'll look like this. And once again, right smack dab in the middle, same value will be the same value as over here. Just very much steeper and narrower. Okay? Well, what causes that? If it's got the same mean, well, what causes distribution to be narrower and steeper? Well, you might guess it's the standard deviation. That's what makes a difference. The standard deviations will not be the same. Now, and that's the second thing that the central limit theorem has to say. We can easily calculate the mean and the standard deviation of the sample means. First of all, as I already said, the mean of the sample mean distribution is notated. Min may be too small, so let me write it bigger. The way we notate when we're talking about the mean of the sample means is we use mu, but then we use x bar to show that this is the mean of sample means. X bar is the sample mean. And it is equal to the original mu, the mean of the original population. They're going to be the same. We already said that. The standard deviation is what causes the different shape, and so they're not going to be the same. And by the way we notate that, I'll make it bigger so you can read it for sure. We use sigma, again with a subscript of x bar. And this is the standard deviation of the sample mean. But it is not equal to the original standard deviation of the original population. Here's the formula. Let me write it bigger. The standard deviation of my sample mean distribution is equal to, and it's a fraction. It's pretty easy to calculate. On top is simply the original standard deviation of the population. And what we do, we divide it by the square root of my sample size. So the bigger sample I take, the bigger denominator I have. And the bigger my denominator have, the smaller the overall standard deviation of my sample means is. Okay? And that's what causes a steep, narrow distribution. Extremely important information for the rest of this course. My next video will actually do some application problems to see how we apply all this.